I really want to. They do things to set up for that.
We are going to about MRI. Yep. So all magnets have two poles. All magnetism comes from the movement of charge. That's why we do current first. So the reason we deal with current first is because current is what creates magnetism. So even if you had a magnet on your fridge, a magnet on your fridge is magnetic because of the movement of charges in that magnet, the way in which the magnets are aligned. Now, it doesn't have current per se, but the charges are moving around the atom. So the way in which those charges are moving create what we call aligned domains. So the way the big three, College Board's got this stuff split into 6 units. I put it in 3. I call them the big 3: electrostatics, current, electricity, and magnetism. Electrostatics is tricky because it's really our first field force that we've dealt with. We've been dealing with gravity all the way through mechanics, but we never really talked about what a gravitational field actually is. So then you finally start to talk about that with electrostatics, like what is an electric field? So that's when the fields become very real. And then very quickly thereafter, we're doing magnetic fields. So electrostatics, charge not moving, then the charge is moving, you got current, electricity, and now we find that all magnetism comes from current, electricity. And in fact, our current, electricity in the room comes from what we call electromagnetic induction. So moving or changing a magnetic field around a coil of wire. Pretty cool. So we can use electricity to create magnetism. We can also use magnetism to create electricity. So all of our electricity in the room comes from the Stanton plant, which is coal / natural gas, like they're converting it. But what it is a turbine being turned by steam. Even nuclear plants are the same. A turbine is turning steam, or steam is turning a turbine. And when that turbine turns, you're changing, you're spinning a magnet, just like you do at the Science Center when you crank the magnetic, the 2 magnets near the coil of wire. You're generating electricity. You're actually spinning a magnet near a coil of wire. So kind of cool. Electricity creates magnetism. Magnetism, in turn, can help us create electricity. Cool. All magnets have 2 poles. So if the most basic magnet, bar magnet, I'll start with, has a north and a south. Field lines go from north to south. This is called a dipole. Di means 2. There are no monopoles that we know of. It's an episode of The Big Bang Theory where they're trying to go to the Arctic Circle to find magnetic monopoles. He doesn't find them. Sheldon Cooper, PhD. Okay. So all magnets have 2 poles. Even if I go down to the atom and sliver off a little piece of the north end, I'm still going to have, even if I cut it, I'm still going to have a little north and a little south. And I'll still have a field going around. So, okay. So even if I go like, what if I cut off just the very end of the north? I'm still going to have a north and a south. Is that all right? And field lines go from north to south. So a lot of things like electrostatics, field lines don't cross. Field lines move from north to south. North is not positive. South is not negative. But field lines, we say, by convention, move from north to south, like positive to negative. Cool? It can. Good. Ishan says, why couldn't my magnet be like this? And to be honest, some of your like little not donut magnets. Yeah, donut magnets are like that. So a little magnet with a hole in it. This actually might be north and this might be south from the bottom. It all depends on it all depends on the magnet. Horseshoe is a bar turned sideways. A sphere. Generally, what they do with spheres is they make it one hemisphere is more northern oriented and the other hemisphere is south or flipped the other way.
Is it like the charge, or is it like the sound is all condensed? Like what makes it sound like?
Good. Okay, so this is what's a little bit tricky, like what creates the magnet? And this will come up in your, like if for a permanent magnet, we're not getting into like current carrying wires. That's coming, we have a lot to do today. Today is like all the nuts and bolts of all magnetism, because we got to get to motors and generators and all this kind of stuff. So all the basics of magnetism. What we have is an unmagnetized iron. And this is not a side discussion. This is actually your next notes. So she just teed me up for this. It's okay. It helps to have a connection from one paragraph to the next. An unmagnetized iron, well, there's these little things we call magnetic domains. They're like little arrows with only part of an arrow. I don't know why the part of an arrow thing is happening. They are random. Just as random as this discussion. Okay, an unmagnetized iron, my little magnetic domains, which are like little norths and souths. Little norths and souths are random. In magnetized iron or magnetized metals, my domains are not random. And you may see a multiple choice at some point on the college board that looks something like this. And this would be north and this would be south. All the little north ends are on one side, all the little south ends are on the other side. So what happens in magnetized iron is that the domains are aligned. So how does that happen? We can take, you can take an iron nail. Like how is, for instance, just a nail magnetic? Well, a nail by itself, an iron nail is really not magnetic, right? It's like, it's not, I can't stick it to like the side of the table, a metal table, and it sticks, but it will stick to a magnet. Now, why is that? It's like a neutral thing. Well, it reorients. So that's exactly it. So what happens is if I were to bring this in the presence of a magnet, like a north and a south. So this is kind of a side discussion. The official notes are kind of the magnetized iron, unmagnetized iron. But if I brought this in the presence of another magnet, a super, super strong magnet, what would all those little domains do? Well, all these little norths and souths these little guys would all turn away. The southern ends of all these little domains would be attracted to this guy. So what we generally do to create magnetized iron or a magnet on your fridge is put it heavily in the presence of a magnetic field. You don't have to draw what's in yellow. But if I do this, then what's going to happen to all these little domains is they're going to go to the left.
How do you make it stay there?
That's a great question. I actually don't know the answer. How do we get it to stay there? You say freeze it, but it's obviously not frozen per se. But it's a way in which we can get the structure to align. Now it doesn't stay there forever. So like your credit card is this. If you bring it near another magnet, it can become that. So the top one. So sometimes your credit card gets demagnetized or your hotel key or gets demagnetized. What your credit card is a little magnetic strip of like north and south one way and then north and south another way, another way, another way, another way, another way, and it creates like a barcode, right? And so that's what the barcode is. It's different aligned magnetic domains. Now, if I bring a magnet near that, or even my phone, because my phone has a magnet inside due to the speaker, it can begin to, the speaker in the phone has a magnet. It can begin to change or realign those, or just randomize those magnetic domains. which demagnetizes the hotel key or your credit card. Does that kind of make sense? So we just call these little magnetic domains. I'm going to get into a little bit later on, like, where does the domain come from? So if that's the question in your head, it's a great one. Where's the domain come from? We're going to talk about that. But for now, we've got all these little norths and souths, and in magnetized iron, they are all lined up.
Is there something? It's like to get from the division, is that just like it's something randomly aligned.
The original magnet. So interesting. I mean, back a long time ago when 14 Columbus sailed the ocean blue, 92. Yeah, right. Back in the day, it's almost Thanksgiving, I suppose. Back in the day, we had these old magic metals that were aligned. Now the original magnet, suppose in that case, came from the Earth. But there was always one before that. What's that? Yeah, so a compass is just a kind of little, piece of metal with a magnetic field. Most of our magnets now don't necessarily come from a piece of metal that's in the ground. We use, like an MRI machine, we use electricity to create an enormous magnetic field and magnetize something. Does that make sense? You could try anything, you give it a shot. I don't know. I'm gonna choose not to answer. There's a lot of things with magnets. Okay. We talked a little bit about this, I think, in this class about how this chapter is going to be everything from your credit card to the power generation to how you trigger traffic lights as you approach them in your car. So there's a lot to do with magnetism that's more than just your little north-south bar magnets.
No, about the wires.
So what does he believe it is?
He said there are like some small town, like especially in our neighborhood, like small lights where you really like he has timed it, he has tested out before, like when back when we used to live here when he was little and stuff, and he would just like pull forward and then see if it would work, and then you got to a point and then it would work.
I mean, more now that there are some lights that have cameras on them, but most of them are induction. My guess is he just got lucky with the timing. Like you pull forward, and like I keep inching, and now it just happens to be the time is passing. So we're not gonna judge anybody though. Everybody, okay. I've been wrong before. That's fine. Okay. We okay there? Here's the thing about this. We're not going to spend a ton of time on this, but you do need to know the nuts and bolts of magnetic domains. There are multiple choice questions I will show you that have to do with these. Fields moving from north to south, just understanding that. But we're not spending a lot of time on this. Why? Because these magnets that we put on our fridge, we don't use quite as much, right? Well, we do use them in motors, but it's a little bit more simplistic. The thing about these is you can't turn them on or off. You can demagnetize them, and I guess permanently turn it off, but it's not like you can turn it on and off. My toothbrush, which only moves because of a magnetic field and electricity, your toothbrush is this electromagnetism. It has a permanent magnet in there. Great. Every motor, the fan motor in your ceiling, they have permanent magnets in there. And then they've got another magnet that you can turn on and off. Fantastic. So in all the motors in Mr. Dedman's room, your toothbrush, there are magnets in there. You can go into Mr. Dedman's room and stick a screw to all the little motors that are in there. There are permanent magnets. Great. We also need magnets you can turn off. So that's where we're going now.
That is permanent magnets on and off. So like the normal block magnet is.
He said, I am wrong. That's fair. I've been wrong before.
That hard to do, but
Huh.
I don't come from that because. Yeah, so pretty.
Yeah, parent night's already over. Unfortunately, I missed that window. Magnetic field due to a current carrying wire. I don't know what I call this A. This is where we're starting to get into the stuff. Okay. So magnetic field due to a current carrying wire. So now what I'm getting into from last chapter, say I've got a 40-volt battery. I'm just going to put on one little resistor here. And just for super simplicity, I'm going to make that 2 ohms. And I want to know what the field is. Remember in the magnetic field. Oops. My mom's the English teacher. She would say, does spelling count? Okay. Magnetic field due to a current carrying wire. So I've got the little loop of wire and I want to find the magnetic field at point A due to the wire. The math is pretty easy here. The conceptual part will get more and more progressively more difficult. So B is my magnetic field. Why? I have no idea why B is magnetic field. Mu naught is how a magnetic field kind of permeates free space. It's a another constant. It is not it's a constant we'll be using 4 pi times 10 to the negative 7. So that's the mu. It's like mu naught. It's like mu. It's like a little mu. Yeah. It's a little mu. I don't know why we're doing another mu, but this is, I mean, for your thought process, it's our magnetic equivalent of epsilon naught. So if we were doing Gauss, E naught was our thing. Mu naught is our magnetic equivalent of epsilon naught. That's how an electric field kind of permeates through space. This is kind of how a magnetic field moves through space, permeates through space. So you've got your magnetic field is mu naught I over 4 pi r. Now, I made a boo-boo. We're not to the 4 pi r yet. Fixing them. I got white out. I have white out. Who needs white out?
Well, I mean, yeah.
Wait, why doesn't the 2 wire and the 4 pi just show up?
It does somewhat.
In like my notes, I will key like.
Oh, man.
Yeah.
The 4 pi is coming. We're just not there yet. Let's get to a circle here pretty soon. What's that? So it ends up being like a loop. A loop. Good. So here's what happens though, is we don't. If you were to look at this in terms of Gauss, it's almost like looking at like a cylinder in a sense. So the 2 pi r is a little bit tricky. Like my field doesn't radiate out spherically now. Because it's a wire, my field's going to kind of move around it. And it's not even radially outward, but it moves around the wire. It's really kind of tricky. Okay, so like concentric circles, it's going to be like looking at an onion. Okay,
Yeah.
so if I were to simplify this, back to Sophia's point, I for now can call the field due to a wire, a straight wire, 2 times 10 to the negative 7 I over R. Now, this simplification I always do with honors because we really kind of stick to just wires. We don't get into like semicircles and loops and toroids and other kind of crazy stuff and solenoids. But this is kind of a simplification for now for the field due to the wire. Okay. So, pretty easy here. Let me go ahead and give you a little bit of a distance. We'll do 4 centimeters. So my field is pretty easy. It's going to be 2 times 10 to the negative 7. That's the simplification of the mu naught over 2 pi. My current's 20 amps and my R is 0.04. No squaring them. So magnetic fields are interesting. You know, at some point we have to graph stuff. Notice how this is not an R squared relationship. Gravitational field, R squared for my point stuff. Why? Because it's more of the cylindrical thing going on. It's almost more like Gauss with a cylinder where it's 1 over R. It's kind of a little bit more like that. So if I were to graph this field as it moves away from the wire, it's a 1 over R relationship, much like Gauss for a cylinder, not Gauss for a sphere or a point mass for even gravity. It's 1 over R squared as you move away. We okay? Calculators unite. What's our field measured in?
Amps per centimeter.
Coulomb per second.
You could derive it, right? 0.0.
So 1 times 10 to the
Yeah. All right. What? What's my units? It does. I don't remember offhand what they are. We could derive them obviously from what I is here. Your meter, coulomb per second. So then what would it have to be? Meter second per coulomb, maybe? But when do we need our Tesla in there? Teslas. Tesla.
Like Nicole does.
Here.
Elon's.
What's the?
They're 10 to the negative 4 elons.
Wait, what?
It's Tesla. Tesla. T.
Or is that what you do?
What base unit? It's Tesla. It's T. Capital T. So, our tau is going to be more like a funky T. Like RC. Speaking of, you have a new tau in this chapter. A new time constant for a whole new thing. This chapter connects circuits to fields to. What does Tesla break down as? It's that mu naught constant. I can't remember offhand what that is. You guys can fact check me. We can break that down in the next, what's that? Nah. Not for now. We can break it down later. I just can't remember what the, mu naught, is offhand. Okay, we good? So here's the question though. What direction? So this is the field. I am up above a wire. Now look, you would know that current by convention is running clockwise. So if I'm only isolating the top part of the wire and I'm up here above it, the field, well, here's where it gets a little bit tricky and enter our first hand rule. The current's going to the right on the yellow wire. I only want the contribution of the yellow wire. There is a contribution of the bottom red wire as well. The sides are kind of irrelevant, but the bottom wire would be a thing later on. So for now, current in the yellow wire is moving to the right And the field for that is, well, here's where it's tricky. In electrostatics, the field's either towards the wire or away from it. Because in electrostatics, the field's going towards or away. This one, the field is going out of the page. It's shooting out towards you. And that's gonna be a little bit uncomfortable, okay? So my first right-hand rule. First right-hand rule that we're gonna talk about is the field, again, due to a current carrying wire. Yeah. Thumb points with current. You want a different version of this, you go online and find something else. All right. Your thumb points to the current, your fingers curl with the field. So as a right-hander, my left hand has to go into my pocket. If you are a left-hand, actually left-handers do better at right-hand rules than right-handers do. Why? Yeah, you can multitask. Right-handers are terrible at this on test because literally as I'm doing the test with you guys, I make the keys often when you're taking your test. I have to put my pen down, do my right-hand rule, then pick my pen back up because right-handers will be just working it and everything's backwards. What? That's a terrible idea. Okay. No, the only reason I say that that's tricky is because when we start to get into it, we're going to have to do one right-hand rule to find the next one, to find the next one. And when they kind of waterfall on, you're flipping them, and there's one that you actually do need to flip them. And so then it gets kind of messy. So I'm going to encourage you, put your left hand in your pocket or right, left-handers do whatever you want to do. And I'm going to say, hey, look, my thumb is going to the right, up above it, my fingers are curling out of the page. See, what a field looks like is it moves around a wire. And it either moves around it like this, or it moves around it like this. Is it coming out of the page and going back in? Is it coming out of the page and going back in? What's it doing? Well, if my thumb goes direction of current, my fingers are curling out of the page up above. So in this case, up above it, the field, any archers in the house? Okay, got a few? So for signs, you clearly would know that that's up. This is probably down. You've got left. You got right. And then you have archery out of the page, like the tip of the arrow coming towards you. Positive Z, or into the page. So in physics, I don't know, but all of your problems are going to let magnetism, you're going to see X's and dots. Dots mean the field is coming out of you, positive Z. X's mean the field's going into the page, away from you. So away from you into the page. So what I know is as that wire goes to the right, underneath it, the field's curling into the page, and out above it, the field's curling out of the page. I could talk about the field in front going down, but you're not really gonna have to describe like what's the field doing like somewhere out of the page. What we're trying to do in physics here is to talk about what's happening three-dimensionally in two-dimensional space. But you may get some things before I move on to some more stuff. Well, let me go ahead and answer that question first off. The out of the page. So the overall answer to my problem, and then I'll talk a little bit about direction before we move on. 1 times 10 to the 4, and I'm out of the page. Question.
Moment in time, because after time passes, it would move further down.
No, this could be as long as there's current running, that's the strength of the field She's wondering like, would the field change? I mean, as long as the current's constant, my distance from that wire is constant, that field's gonna be pretty constant. Now, that field's gonna fall off as I move farther away with 1/R. It'll still be out of the page, but everywhere above the wire, the field's coming out of the page. Is that okay? What's that? Thumbs going to the right because the current's going right on the yellow part.
Yeah.
And up above it, my fingers are curling out of the page.
Oh, okay. So that's-
One thing you can do with the curling, because like, some students are like, yeah, but it's like curling in. But my thumb is the wire. So maybe point up to where your pointing question is and just tip your fingers. And they're curling out. So sometimes just tipping them. Okay, but to help you with your homework, I'm not going to do this full example, but your homework has one that says something like, you have a wire coming towards you, and you've got another wire going away from you. I'm going to get on to some other stuff here in just a second. I need to do force a little bit, as we have a fairly ambitious day today. It'll say on your homework, determine I'm just gonna, you do you. I just want to set you up for direction. Like, how do you approach it when you have two wires? Because your homework doesn't have just one wire. It's obviously, we're going to jump in a little bit more into that. So what if I have these two wires and the wires are a little bit funky now? They're not like going like this or horizontally on the page. Now it's actually the wire that's moving in the positive Z, the 20, or the negative Z, the 40. So I have these two anti-parallel wires, one coming towards me and one going away from me. And it's saying, hey, what's the magnetic field over here? Mathematically, you guys are fine. 2 times 10 to the negative 7, I'd have to give you some distance, right? So the 20 would go with this distance. We'll call that X. And the 40 would go with this distance, Y. Fine. But the big question here is, what do you do with the two answers? You get your field B from the both of the equations, but what the heck do I do with them? I have no clue. I might be adding them, subtracting them. I don't even know. I've got to first figure out direction. Due to the 20 amp wire, it's like looking at an onion that's been cut and you're looking at the concentric circles. If the wire is coming towards me, the field's either moving around counterclockwise or clockwise. My left hand's in the pocket, thumbs out of the page, my field is moving counter. So what's happening is, for the 20, is the field's moving around it like this. So this gets a little bit tricky, right? So I've got a wire coming towards me. I'm just talking about the 20. Wire coming towards me. The point in question is out to the right. And the direction of the field is up. Oof. I'm going to deal with the 40 in a minute. But the field's up. Why? Because if I draw these concentric circles around this thing, like a rock on a string, and sometimes it helps to actually draw the field, like a rock on a string. If this thing is going around like this, at this moment straight out, I'm moving upward actually.
Looks like a tangent.
Correct.
Notice it's going to the left, moving counterclockwise around.
Thumbs out. My fingers are curling around the wire. Counterclockwise.
Got it.
So the right-hand rules are super important, right? My thumb's coming out of the page. So here's the deal. Your thumb always points in the direction of current. If the current is moving, like, say I've got a wire going upward like this. You don't have to write this. I'm just talking. If my wire is going like this, my thumb's up. What's the field doing over here? It's going into the page. What's it doing over here? It's coming out of the page as it goes around it like this. What's really hard, I think, about magnetism is you're trying to imagine on 2-dimensional space a 3-dimensional field. And that's quite tricky. We don't have to do that. The electrostatics can be as difficult as you want to be. And it's still only 2-dimensional. This is really the first time in physics that you have to kind of deal with 3-dimensional space. Later on, you can get into momentum in 3 dimensions, but it's really not bad. You can do just like vector notation for that. Okay, So I know that my field's going up due to the 20, but what about the 40? The 40 thumbs into the page, field's curling around.
Right.
Yeah, it's going clockwise. So this part gets a little bit funky. And so my field's actually going to the right. So now I know what to do with those. So really the point of this little piece of the lesson is what to do when I find the two fields due to the two different wires individually. In electrostatics, you might add them, you might subtract them, you might do Pythagorean theorem. In this case, I do have to do Pythagorean theorem. I'm going to draw the blue one first. I'm going to attach the red one to it, tip to tail, and I'm going to find my angle and everything else. Is that okay? That'd be the direction of field. There's one like that in the homework. But don't always assume it's going to be Pythagorean theorem. Just for your brain, before I move on to force, what if I had two wires? I'll change the color because it's kind of hard to see. What if I had two wires like this? And I said, what's the field here at A? Still just talking about field, and I'm just talking conceptually. What's the field at A? Well, okay, it looks like from my eye right away that I need Pythagorean theorem. However, due to wire one, the field over at A is just going into the page. Wire two, thumbs right, I'm up above it, field's going out of the page. So I only have an in and an out. Just subtract them. See who's win. See the subtracting them, see who's bigger, see who wins. Likewise, if I'm down here, again, it might look like Pythagorean theorem, but for two down there, the field's in. For one, the field over there, it's in. They're both in. Add them, add them. We good? It's okay? Kind of. So this would be wire one would be in, wire two would be, oh, I did out and in wrong, right? So wire one is in, wire two is out. Okay, but down here, they're both in. Still to the right of wire one, but down below wire two.
Like, down like two, it's like this.
Two, you gotta be like this. It's a little bit weird.
Wait, why do you go like, why do you go like that?
Well, see, okay, the only thing is with wire two, if I put my thumb right and I point down to where it is underneath that wire, I can easily like, yeah, it's out.
Oh, okay, you point
And now I'm
out.
up above it. So down here I'm in. What I will encourage you guys to do, as you're doing this on your page, and I encourage you on your test, hold your paper vertically. It will get really confusing if you're doing this on your table, where now down and into the page look like the same thing. So I'm going to encourage you on your test to hold your paper up with your left hand. Do your thumb right, I'm underneath it, field's in. Or for two, my thumb's right and field's out above it. Actually hold your paper vertically with your left hand and do it. Because sometimes you'll see later on, as you start to do it in like this on your table, now down is actually like towards you. That gets confusing. Okay, we good? Force? This is part B. We are doing all of it today, the entire chapter. Oh, review. There's always review day. Yeah, there it is. Yeah. I'm not a sarcastic person.
Is that the name, this? Or is this part of the question?
Nah. This is new topic. So if the first topic was field, the second topic was force. Now, again, you remember electrostatics, there's only field and force. The problem is we've got a lot of other kind of fish to fry in this chapter. So there are two big pieces. There's force and there's field. Remember in electrostatics, KQ over R squared is your basic field. KQ over R squared was your basic force. We're kind of doing the same thing. The equation, Bill. Bill, okay. Field, what? Okay. So it's a little bit different in terms of like, you don't have the KQ over R squared becoming KQQ over R squared. It's not like I just add in the other piece of a wire. To get from Tesla to Newton, I need a little bit more. So interesting though, you guys were asking me about units earlier. It may be easier to drive it here in terms of a Newton. A Newton is a Tesla Coulomb per second meter. So that means Tesla, right? You guys with me? So Tesla is Newton second over Coulomb meter.
You don't have to do all the way.
You don't have to do that. And then you could break that down even more because a Newton is a kilogram meter per second squared. So there's a little bit more base in there if you want to go a little bit further with it. But anyway, that's Coulomb meter, Newton say. Somebody was asking me about Tesla earlier. Okay, so there we go. That's a good way to derive it in terms of newtons. Magnetic force on a wire in a field. Okay, so what if
It's like, I don't even know if they're gonna- Just be a strikeout, I just see it hit, but
Lynn,
just-
here's this, here.
I don't know.
Okay. Okay, wait.
okay. So the length isn't necessarily just the length of the wire because I might not have the entire wire saturated by the field or in the field. So what happens is now, this is a little bit tricky. What if I've got a field created by something else? And soon you'll see how I build. Pretty soon we'll say, well, what if this wire is creating the field and this other wire is in that field and vice versa? Kind of like your mass is in the Earth's, your mass is in the Earth's gravitational field and vice versa. So we'll do wire to wire in just a second, but we'll just say, hey, look, I've got this field created by maybe two magnets. I've got current running on a wire. What is the force on the wire in the field? So the equation, the math is very, very easy. It's just BIL. So in this case, B is millitesla. So 5 times 10 to the negative 3. The amount of current is 20 amps. And the length of the wire that's actually in the field is 80 centimeters. The what is what? Like this part out here. Like that part of the wire, that length of the wire is irrelevant. So like, how about yellow?
Oh, what is that? So is that part?
That's the 80 centimeters, yeah. Okay, it's a part of the wire that's actually in the field. Okay, so easy math, there it is. But what about direction? Our next right-hand rule. Call it your second one if you want. Now, they may be numbered differently if you go on the line or look somewhere else. Sometimes this is the third right-hand rule. The second's a different one for a solenoid. But I'm going to call it our second. This is right-hand rule for, you can just say RHR for force. And I've got one other little part to do to this problem and then we'll be done. I've got to do it in terms of a charge. What if it's a charge? To help you with your homework. Force on a wire in a field. So my thumb. A little confusing when the pH and F are in the same. Yeah, okay. So Ishan's hitting a really good point we're gonna talk about in just a second. So excuse the F on the field, but everything else looks pretty good. Okay, we all make mistakes. Yeah, I probably don't, it may be ownership. It could own it. It could be possessed. I don't know. Okay. Palm pushes with a force. We good? Okay. To Ishan's point. Why the right hand rule? Here's the hard part for me visually. I kind of get, don't write this down. It should already be in your notes a long time ago. I kind of get why these attract because their fields are working together. Right? They want to work together. They want to go from positive to negative. And I kind of also understand why these are going to repel because their fields are pushing off of each other. Right? So I can kind of imagine that in my head. And I kind of get it, right? Like as I push these together, those fields are going to kind of compress and push off. So I kind of understand why the positives repel here in this case and the negatives and positives, the opposites attract. But here's what's really tricky about this, right? To Ishan's point is that I've got, and you don't have to draw this piece, but I've got a field that's moving downward. And at the same time, I got a field that's going around this thing like this, where it's coming like out of the page above, into the page below. So I've got a field going this way and a field going around in a circle. What in the world's the result? So it gets a little bit confusing, right? Like some of the field might be canceling, but this is a little bit weird because like field from the wire up above is perpendicular. We know that those two things really don't go together.
They add together.
But like out here in front, it's like adding and back behind it's subtracting. But let's see what happens. Thumb goes in the direction of current. My fingers point not with the field that it's creating the wire, but the one that it's in from somebody else. Thumb's right, field's down, my palm pushes with the in, forces in. No, you only get to see it one time, it's over. It's in. So it's that number, blank newtons in. And that's hard. So my thumb goes in the direction of current. My fingers are in the direction of field that it's in, which is down. This gets really awkward on test day. And my palm pushes with the force. So I'm not worried about the field that I'm creating now. I want the field that I'm in. So my thumb is right. The field that it's in is pointing down. Your palm is pushing into the page, away from you, but into the page.
Yeah, then the force would be going this way.
Yeah. So the easier one, I suppose I could have given you a nicer one to do with your hand, is if the north were this way and the south were this way, and the field's moving up between there, and then I run a wire through it with current going to the right, my thumb's right, field's up, the force is out of the page.
Why?
You know, one way I like it, she said, how does it make sense? Let's go. I don't know if you heard Brooks's discussion earlier, like up above and below, the fields are perpendicular to each other. So that doesn't do a lot for me. But I like to think about this, and this may or may not be right. Somebody online can judge me. But in terms of what's happening in front and behind, in front, the fields are adding together. Behind, in the page, the fields are canceling out some. The field for the wire is going up, while the field for that thing is going down. So out in front, you've got an increase of field. In here, you've got subtraction of field, decrease of field. So I've got no real change at top and bottom, but I have like a compression of field in the front, less field in the back. So to me, it's like a high to low. Everything in the universe moves from high to low, and I have this like increase of field in the front and a decrease of field in the back, and so it's kind of in a sense pushed from high to low. Because my field for the wire is going into the page below.
Yeah.
Up behind it, up behind it, like in there, out, nothing, down.
Yeah, but
So-
if it's canceling out like doing this, right, like when in a normal wire, right? Not canceling out, but like it's all, it's
Going around,
It's going around.
and it's going up behind it and down in front.
And you put something down, is it gonna go like down and then left side, down, so then it's gonna come down?
No. You wanna do one down? What if I took and put, we can do it down. Let's do probably the easiest one to do with your hand. Now, this is gonna mess with your eye a little bit, so I don't start with this one. But what if my field looks like this? Now, what's creating this field? Some north out here and some south in there. Right? So I've got this field that's moving into the page. And what if I run a wire straight through that? Now, why this one is not good for your eye and really not good for early learning them is because students will look at it and be like, that can't be the field for that wire. And I 100% agree with you. That is not the field for the wire. I can't have a field that's going in above and in below. The field for the wire is going in above, that's true. But it's coming out below. But for force, that wire is in somebody else's field. I'm not worried about its own field, which is going, again, in and out around like this. My thumb's left, the field's into the page, the force on this wire is down. But in a minute ago, my field was up and it goes in. Well, my field was down, it was out.
Why
Or-
is it sideways? Like why is it going up? Like in this one, why is it going up and down? Why is it going in my direction?
Something's creating it. So back to like, if I have a north here and a south here, these two magnets, I got two magnetic dipoles. And but between them, I'm creating a field that looks pretty much like this. And there's a little bit of curve going on over here, but in here, in the middle, I'm looking at pretty much to the left to right. If I then run, this is where it gets a little bit tricky. I'm gonna mess your eye a little bit more on this one. What if I run the wire like into the page here? So rather than running the wire straight up through the field, I'm gonna run it into the field, like this. My wire's like horizontal. So my thumb goes into the page, that's not B. B is the red part, I apologize. That's my eye. This is my eye. My B is in black. So if my eye is current is going into the page, my thumb's in, field's to the right, forces down. But what's kind of cool about this, and I think kind of confusing, is that I can switch the direction of current on this thing and cause it to levitate, but nothing is going up, right? So like to levitate my wire, I don't need a field that's up. And why that's really confusing is in electrostatics, to levitate a proton, you need a field upward on that proton. To levitate an electron, you need a field downward, just the opposite, fine. But here what's really confusing is I got a field going this way, a wire going this way, and what does it want to do? It wants to actually levitate upward. And that's pretty confusing. Back to Ishan's point, what's really, really confusing is to try to think about the field going around the wire counterclockwise while it's in this field that's from left to right. And so now I'm like, what the heck? But again, what I kind of like to think about is that, hey, look, down here, the field's additive. Up here, the field's kind of subtracting or negating. Whereas here on the sides, it's perpendicular and probably not doing anything. So if I look, I have an increased field here, no decrease of field here, thumb's right, Field's, to the right, field, I'm sorry, thumbs out, field's right, force is up.
What's the what on what?
Force of the field on the wire.
Is high fuel on the low.
What does that wire want to do? You let that wire go, it's gonna bow upward. That's the way I like to think about it physically.
That's the thing, it feels like why is it actually gets comparable? Like if you actually. like
That part is, yeah, and I like to look at it as like compression of field. Not as much.
Do the right thing.
Just do the right thing. Last little bit here. This is part of B. If this is B part 1, this is B part 2. As I wrap this up, the good news is the homework's not very long and you've got till Sunday night to do it. So, but I do want you to have all your tools ready to go. This is still force, so I want to call it B part 2. But it's a little bit different. I'll go ahead and move away from my PHs for a minute. Right. I'm gonna flip it. I think in your homework, the field is going like into the page, a bunch of X's. Like positive Z and negative Z? I don't know.
It's wired, it's like, but it's not both of it, right?
Okay. Last little bit here to wrap up. I'm shooting a charge into a magnetic field. So Aspire goes to University of Florida, Gainesville often to do
JSHS.
right, that symposium. And I have toured the what do you call it? The lab for the mass spectrometer. And what's kind of cool about a mass spectrometer is that you're going to separate out charged particles with different masses based on how they're going to accelerate in the magnetic field. So you have basically like a thing that accelerates charged particles and then it kind of bends. And the idea is that when it begins to bend like this, small masses are going to do this and big masses are going to do that. But the way in which we cause them to accelerate around the corner, meaning just change directions, not speed up, is to use magnetic fields. So we can use magnetic field in these charged particles and cause them to accelerate and centripetally. So we get like a semicircle. So what happens when this charge enters the field? Well, I know that a current carrying wire is very much like charge moving. That's what it is. It's coulombs per second. So even if I isolate just one charge in, you guys ever heard of Fermi? Like, yep. Fermi. Next door, there it is. The CERN supercollider. Anytime you're doing these particle accelerators, they're just using the electric fields and magnetic fields to move particles, right? And accelerate them and turn them. And so, okay. So if I know if a wire with current carrying wire experiences force, then obviously a moving charge would. My equation is going to change a little bit. I don't have BIL, but I do have QVB, where this is charge, velocity, and field. And you can see how the unit-wise, it's coulombs, meters per second, Tesla, whereas your other one, BIL, was Tesla coulomb per second meters. So guess what? Probably the same thing, right? Beautiful how physics works out. So my force is QVB. What's going to happen? Well, for this guy, let's just wrap this up. My charge, because it's a proton in this case, is 1.6 times 10 to the negative 19. My velocity is given 3 times 10 to the 5th. And 8 millitesla. that is gonna give me the strength of my force, which is probably gonna be really, really small, but maybe not relative to a mass of 10 to the negative 27. So could be really huge. Yes, as the charge enters that field, yeah. I'm gonna shoot a charge into a field. Now, again, the field moving out of the page is just an orientation, right? There's a north in here and a south in here. I very easily could turn that this way, just like my one a minute ago, and say, hey, the north is up top, and I'm gonna shoot it in like this. Right? So that all this is doing is changing the perspective of my direction. So whether or not the field's going, does that make sense? Like that there, that field is the exact same as if I just took this and rotated 90 degrees.
Yeah.
Okay? Where the arrows would be coming towards me, same thing. Take this, rotate the whole thing 90 degrees. This is still going right, but the field's coming out. My right hand rule, guess what? Your thumb, current, the charge moving, the velocity. My fingers point the direction field is in. My palm pushes through the force. This one, thumb's right, feels down, force in. That one, thumb's right. Feels out, forces down. When this enters the field, it's going to want to go down. So my force direction will be down. Now here's what's really cool, just to connect you to the last question or one of the last questions of the homework. It is initially down, but here's what's a little bit tricky with this. As it starts to go down, now let's say at this moment right here, as it gets pushed downward, is the force like gravity? Does it stay down? Well, now at this moment, tangent to the curve, my velocity is there. So initially, let me go back even. My initial force was down. Let me put that over with where that was actually happening. My initial force right at this moment was down. But what about like at this moment right here? My thumb is down to the right. My field is out of the page. The force is straight down?
No, it's like down to the left.
Oh, it's like this. And then it goes like this, and it's like this. And it's like this, it's centripetal. So watch for FC, mv squared over r, and call it force magnetic, whatever you want to call it, QVB. Watch for these two things having to work together. Because the QVB becomes a centripetal force